May 5, 1945, 9,000 feet above the Oregon forests near Bly. Reverend Archie Mitchell watched in horror as his pregnant wife Elsie and 5 Sunday school children gathered around what appeared to be a large paper balloon tangled in the trees. Moments later, an explosion shattered the peaceful spring morning, killing Elsie Mitchell and all 5 children instantly. What they had discovered was the deadly payload of a Japanese Fugo fire balloon that had traveled over 6,000 miles across the Pacific Ocean, part of a weapons system that American military experts had dismissed as scientifically impossible. The balloon that killed the Mitchell family represented the culmination of a revolutionary warfare concept that Japanese engineers had developed in absolute secrecy. While Allied intelligence agencies focused on conventional threats, Japan had quietly launched over 9,000 intercontinental balloons carrying incendiary and explosive devices designed to terrorize the American mainland and ignite catastrophic forest fires across the western United States. 6,300 miles. The distance that Japanese fire balloons traveled from their launch sites on the eastern coast of Honshu to impact points scattered across North America represented the longest-range weapon attack in human history up to that time. The balloons rode the jet stream winds that Japanese meteorologists had discovered and weaponized years before. Allied scientists understood these high-altitude air currents even existed. This was the moment when unconventional thinking demonstrated that innovative approaches to warfare could achieve strategic results that conventional weapons could not accomplish. The balloon weapon that military experts had ridiculed as primitive and ineffective had become the world's first intercontinental weapon system, striking terror into American civilians and forcing massive defensive resources away from the Pacific War effort. The story of how Japan's Fugo fire balloon campaign nearly succeeded in bringing the Pacific War to American soil doesn't begin with advanced technology. It begins with desperation, scientific innovation, and the willingness to challenge every assumption about the limitations of balloon warfare. To understand why the Fugo program represented such a revolutionary threat, you must first understand the strategic situation that drove Japan to attempt this unprecedented form of intercontinental warfare. By 1944, Japan faced an impossible strategic situation that conventional military approaches could not address. American bombers flying from bases in the Mariana Islands were systematically destroying Japanese cities, while the Imperial Navy could no longer protect the home islands from invasion. Japanese military leaders recognized that only unconventional weapons could shift the strategic balance and force America to negotiate rather than pursue total victory. The inspiration for balloon warfare came from a meteorological discovery that Japanese scientists had made years before their American counterparts recognized its significance. Major Oishi Wasaburo, a meteorologist with the Imperial Army, had identified high-altitude wind currents that flowed from Asia toward North America at speeds exceeding 100 miles per hour. These atmospheric rivers, later known as the jet stream, provided a natural highway for intercontinental attack. Traditional military thinking dismissed balloon weapons as ineffective due to their inability to reach targets with precision or carry significant destructive payloads. Japanese engineers realized that precision was unnecessary if the goal was to create widespread panic and force Americans to divert resources from offensive operations to homeland defense. Terror, not military destruction, became the primary objective. The technical challenges involved in creating intercontinental balloons exceeded anything previously attempted in aviation history. The balloons needed to maintain flight for up to 70 hours, while crossing the Pacific Ocean at altitudes where temperatures reached 60 degrees below zero, and atmospheric pressure was a fraction of sea-level conditions. No existing balloon technology could survive such extreme conditions. The atmospheric science required to understand jet stream behavior involved complex meteorological analysis that Japanese scientists had conducted in secret for over a decade. Major Oishi Wasaburo's weather research had identified wind patterns at altitudes between 30,000 and 35,000 feet that consistently flowed from Asia toward toward North America at speeds that would enable intercontinental balloon flight. Wind velocity measurements conducted by Japanese meteorological stations revealed jet stream speeds that regularly exceeded 150 miles per hour during winter months, when atmospheric conditions created the strongest high-altitude currents. These measurements provided the foundation for calculating balloon flight times and payload requirements for successful intercontinental weapons delivery. Atmospheric pressure calculations demonstrated that balloons operating at jet stream altitudes would experience pressure conditions less than 10% of sea-level atmospheric pressure. These extreme conditions required balloon envelope materials and construction techniques that could maintain structural integrity under near-vacuum conditions while carrying significant payload weights. Temperature analysis revealed that balloons flying at intercontinental altitudes would encounter sustained temperatures as low as -60 degrees Fahrenheit that would affect all balloon components including envelope materials, payload devices, and control mechanisms. Japanese engineers needed to develop materials and systems that could function reliably under extreme cold conditions. Major General Tsuyoshi Kusaba, commanding the Japanese Army's Special Balloon Regiment, supervised development of the Fugo system through a combination of traditional Japanese craftsmanship and innovative engineering solutions. The program operated under absolute secrecy with participation limited to personnel who had sworn blood oaths of silence about the balloon weapon development. The organizational structure of the Fugo program incorporated multiple research and development teams working on different aspects of balloon technology without knowledge of the complete weapon system. Compartmentalized development prevented security breaches while enabling rapid progress on technical challenges that required specialized expertise. Personnel selection for the balloon weapon program emphasized technical competence and absolute loyalty to ensure operational security throughout the development and production phases. Military security officers conducted extensive background investigations of all personnel involved in Fugo development to prevent intelligence leaks that might compromise the program. Security procedures implemented for Fugo development included isolation of manufacturing facilities and restriction of personnel movement to prevent casual observation of balloon weapon production. Workers lived in controlled housing and were prohibited from communicating with family members about their activities during program participation. Resource allocation for balloon weapon development required careful management of strategic materials that were increasingly scarce due to Allied bombing campaigns and naval blockades. Japanese engineers needed to design balloon systems that could achieve intercontinental performance using only materials available within Japan's shrinking industrial base. The balloon envelope design incorporated revolutionary materials and construction techniques that pushed Japanese manufacturing capabilities to their absolute limits. Engineers developed a laminated paper called washi that combined traditional Japanese papermaking with modern chemical treatments to create materials stronger than conventional fabric, while remaining light enough for high-altitude flight. Washi paper development involved collaboration between traditional Japanese papermakers and modern chemical engineers to create materials with unprecedented strength-to-weight ratios. The paper incorporated multiple layers of different fibers that were bonded using chemical treatments that provided flexibility at extreme temperatures while maintaining structural integrity. Chemical treatment processes for balloon envelope materials utilized rare compounds that were difficult to obtain under wartime conditions. Japanese chemists developed substitute formulations using domestically available materials that provided adequate performance while avoiding dependence on imported chemicals that Allied blockades had made unavailable. Strength testing of balloon envelope materials included evaluation under simulated high-altitude conditions using pressure chambers and temperature testing equipment that replicated the extreme environments that intercontinental balloons would encounter. Testing standards exceeded normal aircraft material requirements by substantial margins. Durability analysis revealed that balloon envelope materials needed to maintain flexibility and strength through repeated expansion and contraction cycles, as atmospheric pressure and temperature changed during flight. The materials required resistance to ultraviolet radiation, ozone exposure, and mechanical stress that conventional materials could not provide. Manufacturing the balloon envelopes required mobilization of Japan's traditional paper craftsmen, who possessed skills that modern industrial methods could not replicate. Thousands of schoolgirls worked in secret factories, assembling balloon sections using techniques that their grandmothers had perfected for making ceremonial kites and lanterns. The combination of ancient craftsmanship and modern engineering created balloon envelopes of unprecedented strength and reliability. Workforce mobilization for balloon production involved recruiting skilled craftspeople from traditional industries, including paper-making, kite construction, and textile manufacturing. The workers received specialized training in precision assembly techniques required for balloon envelope construction while maintaining secrecy about the military applications of their work. Production facilities for balloon manufacturing were established in remote locations away from major industrial centers to prevent detection by Allied reconnaissance aircraft. The facilities utilized traditional construction methods and materials to avoid revealing their military significance while providing adequate working conditions for precision manufacturing. Assembly procedures for balloon envelopes required hand-stitching techniques that ensured uniform seam strength throughout the envelope structure. Workers used traditional Japanese sewing methods that created seams stronger than machine-sewn alternatives while maintaining the flexibility required for high-altitude operations. Quality inspection of balloon envelopes involved detailed examination of every seam and surface to identify potential failure points that could cause catastrophic balloon loss during intercontinental flight. Inspection standards required rejection of envelopes with any visible defects that might compromise structural integrity under operational conditions. Training programs for balloon manufacturing workers emphasized precision and attention to detail that exceeded normal industrial standards. Workers learned specialized techniques for handling delicate materials and creating seams that would maintain strength under conditions that would destroy conventional textile products. Quality control for balloon manufacturing established testing standards that ensured each envelope could withstand the extreme conditions of intercontinental flight. Every balloon underwent pressure testing, temperature cycling, and structural analysis that verified its ability to carry payloads across the Pacific Ocean without catastrophic failure. Pressure testing procedures involved inflating completed balloon envelopes to pressures that exceeded expected operational conditions, while monitoring for leaks or structural weaknesses. Testing equipment included precision pressure gauges and monitoring systems that detected minute pressure losses that could indicate potential failure points. Temperature testing exposed balloon envelopes to extreme cold conditions that simulated high-altitude environments while evaluating material flexibility and seam integrity. Testing chambers utilized refrigeration equipment to achieve temperatures approaching those encountered during intercontinental flight at jet stream altitudes. Structural analysis included load testing that verified balloon envelope strength under payload conditions that would be encountered during operational missions. Testing procedures simulated the stresses of carrying incendiary and explosive devices while maintaining flight capability throughout the predicted mission duration. Documentation procedures for balloon testing created detailed records of performance characteristics for each envelope that passed quality control inspection. The documentation enabled tracking of balloon performance and identification of manufacturing variations that might affect operational reliability. Statistical analysis of balloon testing results provided data that influenced manufacturing procedures and quality control standards. Engineers used testing data to refine production techniques and identify optimal material specifications for improved balloon performance and reliability. Incendiary device development required creating reliable ignition systems that would function after prolonged exposure to extreme environmental conditions during intercontinental flight. The devices needed to withstand temperatures, pressure variations, and humidity changes while maintaining readiness to ignite upon impact or timer activation. Chemical composition analysis for incendiary devices identified compounds that would burn reliably under various conditions, including high humidity and low oxygen environments. Japanese chemists developed incendiary formulations using domestically available materials that provided adequate burning characteristics for forest fire initiation. Ignition system design incorporated multiple backup mechanisms to ensure reliable operation despite exposure to extreme conditions during balloon flight. The systems utilized mechanical, chemical, and electrical ignition methods that provided redundancy against failure of individual components. Timer mechanisms for incendiary devices required precision clockwork that could operate reliably after exposure to extreme cold and pressure variations. Japanese clockmakers adapted traditional timepiece technology to create timing devices that maintained accuracy under conditions that would stop conventional clocks. Explosive device development focused on creating anti-personnel weapons that would detonate when disturbed by anyone discovering balloon payloads after landing. The devices incorporated sensitive triggering mechanisms designed to kill civilians who might investigate balloon wreckage. Triggering mechanism design for explosive devices utilized pressure-sensitive systems that would activate when balloon payloads were moved or examined. Japanese engineers developed triggering systems that remained dormant during flight, but became active after landing to maximize civilian casualties. Safety procedures for payload handling during balloon preparation required specialized training for personnel who assembled and installed explosive and incendiary devices. Workers needed to understand the lethal nature of the devices while maintaining security about their intended targets and effects. Incendiary device development focused on creating reliable ignition systems that would function after exposure to extreme cold and atmospheric pressure variations during transcontinental flight. The devices incorporated multiple backup ignition systems and chemical compositions that remained stable under conditions that would destroy conventional explosives. The balloon control system represented the most sophisticated aspect of Fugo technology, incorporating an automatic altitude control mechanism that maintained optimal flight altitude throughout the intercontinental journey. The system used atmospheric pressure sensors to activate ballast release mechanisms that kept balloons within the jet stream corridor for maximum range and speed. Ballast release mechanisms operated through ingenious clockwork timers that had been calibrated to maintain proper balloon altitude during the predicted 70-hour flight time to North America. The mechanical systems required precision manufacturing that exhausted Japan's remaining stockpiles of strategic materials, including aluminum and precision steel components. Launch procedures for Fugo balloons involved careful timing to coordinate with favorable jet stream conditions that meteorologists predicted would carry the weapons to American targets. Launch teams monitored atmospheric conditions continuously and released balloons only when wind patterns provided optimal flight paths toward the North American continent. The first Fugo launches began in November 1944 from sites along Japan's eastern coast, including locations near Sendai and other cities that provided access to jet stream currents. Launch teams released balloons during nighttime hours to prevent detection by American reconnaissance aircraft that might reveal the balloon weapon program to Allied intelligence. Initial launch operations proceeded smoothly with balloons disappearing into the darkness as planned, but Japanese intelligence had no method for determining whether the weapons reached their intended targets or achieved their destructive objectives. The intercontinental range that made Fugo balloons strategically valuable also prevented assessment of their tactical effectiveness. American detection of Japanese fire balloons began with scattered reports from civilians and military personnel who discovered balloon wreckage across the western United States and Canada. Initial reports were dismissed by military authorities who could not believe that Japanese weapons had reached North American territory through atmospheric flight. The first confirmed Fugo discovery occurred on November 4, 1944, when a United States Navy patrol discovered balloon debris near San Pedro, California. Technical analysis revealed construction techniques and materials that clearly indicated Japanese origin, forcing American authorities to acknowledge that Japan had developed intercontinental weapons capability. Military censorship immediately classified all information about Japanese balloon weapons to prevent public panic and deny Japan intelligence about the effectiveness of their intercontinental attacks. Newspaper editors received strict instructions to suppress all reports about balloon discoveries or related incidents that might reveal details about the Fugo campaign. Technical analysis of recovered balloon components revealed sophisticated engineering that impressed American experts who had underestimated Japanese technological capabilities. The automatic altitude control systems and precision manufacturing exceeded expectations for Japanese wartime production capabilities under severe resource constraints. Weather analysis conducted by American meteorologists to understand balloon flight patterns led to discovery of the jet stream phenomenon that Japanese scientists had identified years earlier. American recognition of high-altitude wind currents came through reverse engineering of Japanese weapons rather than independent scientific research. The strategic implications of successful Japanese intercontinental attacks forced fundamental reassessment of American homeland vulnerability and defense requirements. Military planners realized that conventional defense approaches could not protect against weapons that traveled through atmospheric regions beyond the reach of interceptor aircraft or anti-aircraft guns. Defensive measures implemented against Fugo balloons included deployment of fighter aircraft for interception missions and establishment of observation posts throughout the western United States to report balloon sightings. However, the balloons flew at altitudes and speeds that made interception extremely difficult even when aircraft could locate the targets. Forest Service personnel received emergency training in balloon weapon identification and disposal procedures, as authorities recognized that most Fugo balloons would land in remote wilderness areas where civilian discovery was likely. The training emphasized the deadly nature of both explosive and incendiary devices that balloons carried. Public safety measures included classified warnings to law enforcement and emergency services about balloon weapons, while maintaining strict censorship to prevent public awareness that might cause widespread panic. Authorities walked a careful line between preparation and secrecy that reflected the unprecedented nature of the threat. The psychological impact of Japanese intercontinental weapons capability affected American civilian morale even though censorship prevented widespread public knowledge of the balloon attacks. Rumors and speculation about mysterious explosions and forest fires created anxiety about homeland vulnerability that Japan had intended to achieve. Military resource allocation for balloon defense diverted aircraft, personnel, and equipment from Pacific operations, as American commanders struggled to address a threat that conventional military doctrine had not anticipated. The defensive measures validated Japanese strategic calculations about forcing resource diversion through unconventional attacks. Intelligence analysis of Japanese balloon technology revealed advanced understanding of atmospheric science and precision manufacturing that challenged assumptions about Japanese technological capabilities under wartime conditions. The balloon weapons demonstrated innovation that conventional intelligence assessments had failed to predict. Counterintelligence operations attempted to determine the scope and objectives of Japanese balloon attacks while maintaining operational secrecy that prevented Japanese assessment of their weapons' effectiveness. American authorities recognized that revealing defensive measures would provide Japan with intelligence about balloon performance and targeting accuracy. The tragic incident at Bly, Oregon on May 5, 1945, represented the only confirmed American fatalities from Japanese balloon weapons and demonstrated the lethal potential of devices that most military experts had dismissed as ineffective. The deaths of Elsie Mitchell and the 5 children provided sobering evidence of Fugo lethality. Investigation of the Bly incident revealed that the balloon had carried both incendiary and explosive devices designed to maximize casualties among anyone who discovered the weapon after landing. The placement of anti-personnel devices alongside incendiary weapons reflected Japanese intent to kill American civilians rather than limiting attacks to military targets. Media censorship prevented public reporting of the Bly incident, despite its significance as the first enemy attack on American mainland territory since the War of 1812. Military authorities maintained absolute secrecy about the civilian casualties to prevent panic and deny Japan confirmation of their weapons' effectiveness. Memorial services for the Bly victims proceeded under military security that prevented public acknowledgement of how the deaths had occurred. The families received classified briefings about the circumstances, while public records falsified the cause of death to maintain operational security about Japanese balloon weapons. Scientific analysis of Fugo balloon technology conducted after the war revealed engineering sophistication that exceeded contemporary American capabilities in several critical areas. Japanese engineers had solved technical problems that American researchers had not yet attempted, including automatic altitude control and intercontinental navigation using atmospheric currents. Post-war interrogation of Japanese balloon weapon developers provided insights into the scope and objectives of the Fugo program that confirmed American fears about the strategic threat posed by intercontinental weapons. Japanese engineers had planned expanded balloon campaigns with biological and chemical warheads that would have devastated American agriculture and population centers. The industrial capacity required for Fugo production demonstrated Japan's ability to mobilize traditional crafts and modern technology for military purposes, despite severe resource shortages and Allied bombing campaigns. The balloon program proved that innovation could overcome material limitations through ingenious design and manufacturing approaches. Educational programs developed after the war to analyze Fugo technology influenced American understanding of unconventional warfare and atmospheric science. Military schools incorporated lessons learned from Japanese balloon weapons into curricula that emphasized innovative thinking about threats that conventional doctrine could not address. International recognition of Japanese balloon weapon capabilities influenced post-war treaties and agreements about intercontinental weapons development. The Fugo program established precedents for atmospheric weapons delivery that affected subsequent arms control negotiations and strategic defense planning. The human cost of Japanese balloon warfare included not only the direct casualties at Bly, but also the psychological impact on American civilians who lived with knowledge that enemy weapons could reach their communities without warning. The invisible threat of atmospheric attack created anxiety that conventional warfare had not previously imposed on American homeland security. Strategic assessment of Fugo effectiveness revealed that Japanese balloon weapons achieved significant psychological and defensive objectives despite limited material damage to American targets. The balloon campaign forced resource diversion and created homeland vulnerability concerns that validated Japanese strategic calculations about unconventional warfare. Technological innovation demonstrated through Fugo development influenced post-war aerospace research and development programs as American engineers studied Japanese atmospheric flight techniques and automatic control systems. The balloon weapons provided insights into high-altitude flight that contributed to subsequent space exploration and intercontinental missile development. Memorial recognition of the Bly incident victims came only after wartime censorship restrictions were lifted, and the public could learn about the circumstances of their deaths. Elsie Mitchell and the 5 children became recognized as the only American civilians killed by enemy action on mainland United States territory during World War II. The Bly Incident Memorial, established at the location where the balloon explosion occurred, serves as a reminder of the global reach of modern warfare and the vulnerability of civilian populations to unconventional weapons. The memorial acknowledges the sacrifice of innocent victims who died from a weapon that traveled further than any previous military device. Educational programs developed around the Bly Memorial teach visitors about the Fugo balloon campaign and its significance as the first intercontinental weapon system. The programs emphasize the innovative nature of Japanese balloon technology and the strategic implications of atmospheric weapons delivery. Historical preservation of Fugo balloon fragments and related artifacts provides physical evidence of Japanese engineering capabilities and the global scope of World War II combat operations. Museums display balloon components alongside documentation of the Intercontinental Campaign that brought enemy weapons to American territory. Research programs continuing to study Fugo technology focus on atmospheric science applications and historical analysis of unconventional warfare development. Scientific institutions examine balloon design principles and atmospheric flight techniques that influenced post-war aerospace development. May 5, 1945. 9,000 feet above the Oregon forests near Bly. The Japanese fire balloon that killed Elsie Mitchell and 5 innocent children had traveled over 6,000 miles to demonstrate that innovative thinking could overcome impossible odds and challenge conventional assumptions about warfare limitations. The weapon that experts had called useless had achieved strategic objectives that conventional attacks could not accomplish. The psychological transformation was complete. Americans realized that their homeland was not invulnerable to enemy attack, and that unconventional weapons could threaten civilian populations despite overwhelming military superiority. The balloon that seemed primitive and ineffective had become proof that innovation could trump conventional military power. That's how Japan's useless balloon weapon proved that scientific innovation, combined with desperate determination, could achieve strategic results that challenged fundamental assumptions about warfare and homeland security. The Fugo fire balloon campaign demonstrated that the longest range doesn't always require the most advanced technology, and that sometimes the most dangerous enemy is the one you never see coming.